AI image generation is, at its very core, a highly structured mechanical assembly line of data driven by mathematical processes. To understand how this machinery operates, we can look at ComfyUI. It is a visual, node-based programming interface that exposes the raw components and connections of the image generation pipeline. This diagram maps the macro stages of the generative pipeline. The process begins with a human prompt, travels through a text encoder, passes into the generation engine, and finally moves through a decoder to produce the save image output. Following this pathway shows how subjective human language is converted into numbers, how those numbers predict static noise, and how that noise resolves into a high-fidelity image. Mastering this specific node graph provides the visibility required to move beyond trial-and-error prompting and begin controlling the system's underlying logic. The pipeline begins at the clip text encode node. This node handles the translation from human grammar to the numerical data a computer requires. This animation illustrates the first step, tokenization. The AI relies on a fixed dictionary to break a raw string of text into smaller, mathematically manageable chunks called subwords. The system assigns a unique ID number to each token. However, an ID number alone lacks semantic weight. A computer does not inherently know that apple and banana belong to the same category. The text encoder passes IDs through an embedding layer, mapping tokens to spatial coordinates where similar concepts cluster tightly. Words change meaning based on context. In the bank of the river, the system scans surrounding tokens. Recognizing water, the bank vector recalculates its trajectory toward nature. By the time data exits the text encoder, subjective human language has been converted into precise geometry that the machine can calculate. To understand why generation math is intensive, we look at the end of the pipeline, the VA decode node, and the physical constraints of pixel space. A standard 512 by 512 digital display contains hundreds of thousands of pixels. Zooming in reveals every pixel is divided into red, green, and blue subpixels, scaling from 0 to 255. Generating one image requires calculating specific values for over 780,000 subpixels, navigating millions of color combinations. Running complex diffusion math directly on this raw, uncompressed pixel space is computationally prohibitive, making the generation process extremely slow. The solution is latent space, a compressed mathematical summary of the image that stores only vital structural concepts and shapes, rather than raw pixel data. The variational autoencoder, or VAE, manages this compressed space. The encoder side strips away unnecessary pixel data, forcing the image through a mathematical bottleneck to extract a compact numerical vector. The decoder then takes that compressed vector and expands it outward to reconstruct a viewable pixel space image. Performing the heavy generation math inside this latent space bottleneck is what allows stable diffusion to operate with high efficiency. The actual image generation occurs within the KSampler node, working entirely inside that compressed latent space. Diffusion is the process of generating data by learning how to reverse a gradual noising sequence. During training, a model undergoes forward diffusion. Engineers take clean data and gradually corrupt it with random static until the original image is lost. This process creates training examples that teach the AI exactly what mathematical degradation looks like at different intervals. In the generation phase, known as backward diffusion, the AI is given a canvas of random noise and tasked with reconstructing a realistic image. The underlying neural network functions as a noise predictor. The network analyzes the static, calculates which portion is unwanted noise, and subtracts it, revealing a slightly cleaner structural layer beneath. The sampling steps parameter determines how many times the AI repeats this subtraction loop. As steps progress, the blurry shapes sharpen into a final result. The text embeddings act as the semantic map, telling the noise predictor which patterns to search for within the static. The CFG scale acts as a strictness style, forcing the noise predictor to follow the text embeddings closely, rather than generating its own patterns. This generative process is one of subtraction, where calculated mathematical noise is carved away using semantic coordinates as a guide. When we look at the master pipeline, the entire mechanism operates as a single demystified circuit. Subjective text is tokenized and embedded into mathematical vectors. Those vectors provides a guidance for the noise predictor. which subtracts static inside the compressed latent space bottleneck until the final latent vector is decoded back into a high-fidelity RGB output. This modular architecture allows new components to be added to the circuit, refining the final output. Control net nodes can be injected to enforce structural boundaries, providing the noise predictor with a specific skeletal pose or edge map to follow. LoRa nodes act as lightweight add-ons that alter the model's weights, allowing it to produce specific artistic styles or characters without needing to retrain the core system. By moving past the black box mentality and mapping the node graph's math, users move from guessing to constructing intentional AI generations.